Today we will see in detail the Hermitian operators, that is like position, momentum and energy operators and their property in detail. First of all, we will see what is Hermitian operators. Before going into the details of Hermitian operator, we will see the expectation value. We know the expectation value of an operator A is given by that is A is equal to the inner product of psi A psi. This is the definition for the expectation value. In the integral form, it can be written as the expectation value of A is equal to integral. We know very well that normally the vector is can be represented as complex wave function and A and get vector. So integral psi star A psi dx. So it is in the integral form. It is in Dirac notation. The physical observables are represented by such a expectation value. We know very well. The physical observables are represented by the expectation value. Um, the value of physical observables like position, momentum, and energy must be a real quantity. We know very well it must be a real quantity. So the expectation value of A must be real. Uh, Therefore, for expectation value of A to be real, uh, the expectation value of A must be equal to the complex of the expectation value of A. That is, expectation of A is equal to expectation of A complex A star. So, uh, we will see what this means. In order to the expectation value to be real, we have seen just now that the expectation value of A must be equal to expectation value of A star. This which can be written in the integral form as integral psi star A psi dx is equal to. Now you take complex of this. Psi star of psi is equal to psi. A will become A star and psi will become psi star dx. It is convention to write the complex value first. So it can be written as uh, integral of A psi whole power star into psi dx. So it is in the in integral form. In Dirac notation, it can be written as integral of psi star A psi dx can be written as bra psi get A psi. Similarly, this can be written as integral of A psi, which is a complex, is can be represented as bra vector, that is bra A psi. Of course, this is a get psi. So in the Dirac notation, it can be written as psi get A psi, which is equal to bra A psi get psi. So if the operator A that satisfies these conditions are called Hermitian operators. That is, it can always be flipped over to the other side if it appears in an inner product. That is, uh, it can be flipped from bra vector to get vector or get vector to bra vector. Your result does not change. So this is the basic definition for the Hermitian operator. Now we will see whether the position operator is a Hermitian operator or not. So this is the definition for the Hermitian operator. Now you operate the position operator over get psi. You will get an eigenvalue of x multiplied with the get psi. So the bra psi get x psi can be written as x psi into psi. This is the inner product of psi into psi. X is the eigenvalue of X operator. Now I am flipping this X operator over to the bra vector, that is X is bra X psi into get psi is equal to X star, because bra vector, as I said, is a complex value. So it will become X star psi with the psi, inner product of psi with the psi, which is equal to, since the position is a real quantity, X star must be equal to X. So I can rewrite this as X inner product of psi with psi. Now you can compare these two expressions. That is, when X operator act on get vector, you are getting X psi with psi. Similarly, if you are flipping to X to bra vector, you are getting the same result. That means position operator is a Hermitian operator. Before going into the details of momentum and the energy operator, we will see the differential operator. Basically, the momentum and the energy operators are differential operator, which is multiplied by the factor I h cross. So we will see why that I comes in the momentum operator as well as in the energy operator. So first you take the differential operator. You, A is equal to T by Tx is a differential operator. The basic definition for Hermitian operator is this one we have seen. So the left hand side in the integral form you can write like this: integral over minus infinite to plus infinite psi star a psi dx. So since a is a differential operator, I have replaced a by t by tx. You can see here. So this is in the UDV form. U is psi star, V is psi. So the integral of UDV can be found using the formula UV minus integral VDU. Now you take the left hand side. Left hand side you have U, that is psi star, and then dV. dV is t psi by dx into dx will come. So dx. In the right hand side, u v, that is u is psi star, v is psi, within the limit minus infinite to plus infinite. Minus v, v is psi, I have taken here, because it's a convention that we have to write complex function first. So v du, du is u is psi star, so t psi star over tx. Here, it is well known that the psi star psi, the product of psi star psi within the limit minus infinite to plus infinite will become 0. Uh, if psi is 0 at minus infinite, then psi star will be 0 at plus infinite. So this will be going to be 0 either at the limit minus infinite or at plus infinite. So the only term left out is minus integral t psi star psi dx. So I have taken this here. That is left hand side integral psi star t psi over dx into dx is equal to minus integral t psi star dx psi dx. We will see what how to represent this in Dirac notation. Just now we have seen that the integral psi star t psi over tx into tx is equal to minus integral over minus infinite to plus infinite t psi star over tx psi tx. In Dirac notation, you can write this psi star, since it's a complex function, so it can be represented as a bra vector, and this one, the next one is get vector. In Dirac notation form, it can be written as psi a bra psi into get t psi by tx. Similarly, the right hand side minus I have taken out. Uh, this is a complex value, so it can be represented as bra vector. That is bra t psi by tx. This is get psi. So get psi. So this is the get vector. So this can be represented in the Dirac notation like this. So which is the basic definition of Hermitian operator. However, you must realize that there is a negative sign in the right hand side. That means it is when you flip the differential operator from get vector to bra vector or bra vector to get vector, you will get a negative sign. That means the differential operator is anti-Hermitian, not a Hermitian, it's an anti-Hermitian. Hence, I comes in the momentum and the energy operator, as I said already. The reason for I comes in the both energy and momentum operator is in order to make this operator as a Hermitian. We will see about the energy and momentum operator. Now we will see about the momentum operator. By definition, P is equal to minus I h cross uh, T over Tx. So this is the definition for momentum operator. Now I am introducing in the basic definition of Hermitian operator is this one. Now I am introducing this momentum operator in the get vector side. So psi star integral, this is the Dirac notation. In the integral form, it can be written as integral psi star uh, operator P, momentum operator P is acting on the get vector. That is psi star P psi Tx. It is in the integral form. That is, the momentum operator is minus I h cross t psi by tx. This is the from the definition of the momentum operator. So the left hand side I am keeping as it is. In the right hand side, I am applying this UDV formula as I have done in the case of differential operator. So this will become minus IH cross. This is in the form of UDV, where U is psi star, V is psi. So which is equal to UV. Of course, UV is psi star psi between the limit minus infinite to plus infinite, and minus VDU. Here V is psi, T is psi star over Tx into Tx. So, as we have seen in the case of differential operator, between this extreme limit, either psi will be 0 or psi star will be 0. So, the first term will get cancelled. Only the second term left. Remember that there is one minus here. So minus IH cross, here one minus. So this will become plus IH cross integral psi t by tx of psi star tx. Now we will see what will happen to this expression. So just now we have seen integral psi star p psi tx is equal to IH cross integral psi t psi star over tx into tx. We have seen this. Uh, Now, as I said, is customary to write the complex wave function first. So, the psi star, psi star by tx will come first. Of course, you bring this IH cross because you are going to take complex value of this one. So, this IH cross will become minus IH cross. So if you take complex of minus IH cross, you will get plus IH cross. So I brought just I interchanged the wave functions because of the customary thing. So this complex wave function will come first. That is minus IH cross delta psi over delta x star psi dx. Here, this is the momentum operator. That is, sorry, this is the momentum operator, except this psi. This is the momentum operator. This can be written as momentum operator which act on psi. Of course, there is a complex conjugate. This is momentum operator which is operating on psi. Of course, the entire thing is we are taking complex value into psi tx. Now the integral of psi star p psi dx is equal to integral of p psi star whole power star into psi dx. That is in terms of Dirac notation, it can be written as this complex wave function can be written as vector, that is psi, bra psi, and this is get uh, p psi is a get vector, get p get psi. So in the left hand side it will become psi get p psi. In the right hand side, this complex can be written as a bra vector, that is P act on psi, momentum operator act on psi, bra P psi multiplied with get psi. So it is exactly the definition for the Hermitian operator. Now the momentum operator is Hermitian operator. There is no negative sign. That is the reason why we are introducing, or it is energy operator and momentum operator by definition. You will get one I in order to make it Hermitian. If it is a differential operator, it is anti-Hermitian. In order to make it Hermitian, there is a I factor here. We will see about the energy operator. Similarly, by definition, the energy operator is equal to IH cross delta over delta T. You can apply the same thing, same procedure adopted for the uh, momentum operator, and you can prove that the energy operator also a Hermitian operator like momentum operator. Here I like to highlight some interesting fact. We know by definition P is equal to minus IH cross delta over delta X. Then what is the complex of this one is equal to this minus IH cross will become plus IH cross. That means which is equal to minus negative of this thing, minus P operator P. Similarly, E is equal to IH cross delta over delta T. Then E star must be equal to minus, because this IH cross will become minus IH cross, which is equal to minus E. That means the momentum operator is a Hermitian operator, but not equal to its own complex conjugate. That is a very important point. It is also true for the energy operator. Now we have seen about the energy and momentum operator, and we will see some of the important property of Hermitian operator. In the beginning of my lecture, I told that the eigenvalues of Hermitian operators are real. So we are going to prove that eigenvalues of Hermitian operators are real. By definition of Hermitian operator, psi A, this is the state A, psi A, bra psi A multiplied with get A psi A is equal to, must be equal to A psi A multiplied with psi A. This is the basic definition for Hermitian operator. If A act on psi A, you will get the eigenvalue of A, eigenvalue of A. So this will become psi A with psi A. Similarly, when A act on the bra vector, you will get A star naturally. A star psi A with psi A. You bring this to left hand side, you will get A minus A star into psi a with psi a, inner product of psi a with psi a is equal to 0. However, you know very well that inner product of psi a with psi a is equal to 1 due to orthonormal property. It is equal to 1. You know very well, due to orthonormal property. That means it must be a minus a star must be 0. That means a is equal to a star. So hence we have proved that the eigenvalue of Hermitian operators are always real. That is one of the important property. Now we will see the another important property of Hermitian operators. That is Hermitian operators are always orthogonal. By basic definition of the Hermitian operator, uh, psi, as I have mentioned so many times, when operator flipped over to other side, you will get same result. That means now you consider two state. Wave functions of A state is psi A and B state P is psi P. So here in the left hand side, your Hermitian operator act on the get vector psi P. So naturally you will get an eigenvalue of P. So this can be written as P inner product of psi A with psi P. Similarly, here I have flipped the operator to the bra side. Here it is psi A. When the Hermitian operator act on psi A, you will get eigenvalue of A star. That is a complex. Bra vector is always complex, so you will get A star. Of course, these eigenvalues are real. That also you have to keep in mind. So this will become A star psi A inner product of psi A with psi B. So if you bring this to left hand side, you will get P minus A because the eigenvalues are real. Just now we have seen the proof also. This A star will become just A into psi A with psi P, which is equal to 0. Here you have to keep it in your mind that P minus A is not equal to 0 because P is the eigenvalue of a different eigenfunction and A also different. So it cannot be 0. That means the inner product of psi A with the psi P is equal to 0. So it is simply proved that the different vector, that is inner product of psi A with psi P is equal to 0. That means it is orthogonal. So we have proved that the eigenvectors of Hermitian operators are always orthogonal to each other. Thank you very much for watching my video and supporting me continuously.